All right, so we're still talking about enolates here, and we're talking about a ketone. And the interesting part here is that it actually has two alpha positions, same ketone here, but two different types of alpha hydrogens, all right? So we have an alpha hydrogen here, and we have alpha hydrogen here, and these would actually give you different enolates, as shown below. So why would one happen versus the other? It's actually an interesting kinetic versus thermodynamic phenomenon. So if we just look at these two enolates, let's do some numbering of carbon. So maybe 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. So we're talking about two different alpha positions on carbon 1 and carbon 3. So carbon 1, right, this enolate, we'd actually call this the kinetic enolate. And this would be the thermodynamic enolate. Now, why is that? Well, the enolate that results here is actually more stable than this enolate. Now, why is that? That's a Zaitsev rule kind of problem. The more substituted enolate, so you see, like just like your alkene rules, this is a more substituted enolate. But this is the kinetic enolate, so this is more stable. But this comes from a lower energy, lower activation energy, because it's easier for bases to get to this hydrogen. There's also just more of them. So this is your kinetic enolate. So if you wanted this, you maybe want this to be under cold conditions. Maybe this one to be a little bit warmer, but you can control that with temperature just like you would any other thermodynamic or kinetic phenomenon. So a lot of times, right, if you have double-sided, right, you got to kind of think about what kind of enolate do I want to make, thermodynamic or the kinetic, and you can control that with temperature.